Learning Goals. Welcome to this learning session on index laws, powers, roots, and simplification. In this course, we shall address Introduction to Indices, Basic Laws of Indices, Powers of 0 and 1, Understanding Roots, Applying Index Laws. There will be a quiz at the end to test your knowledge.
Introduction to Indices and Exponents. Indices are a fundamental concept in mathematics, representing repeated multiplication of a number by itself. They provide a concise way to write very large or very small numbers, making complex calculations more manageable. Understanding indices is crucial for various scientific and engineering fields, from calculating compound interest to describing exponential growth or decay. The components of an index expression are the base and the exponent. The base is the number being multiplied, and the exponent, or power, indicates how many times the base is used as a factor. For example, in 2 or 3, 2 is the base and 3 is the exponent, meaning 2 multiplied by itself 3 times. Indices are also known as exponents or powers. The term index comes from the Latin word indica, meaning to point out or show, referring to how the exponent points out the power or frequency of multiplication. The multiplication law of indices. The first fundamental index law states that when multiplying two powers with the same base, you add their exponents. This rule, expressed as am per an equals eighth to m plus n, simplifies expressions significantly. It's essential that the base numbers are identical for this law to apply. For instance, 4 3 4 7 becomes 4 3 plus 7, which simplifies to 4th 10. This law is particularly useful in scientific notation, where large numbers are expressed as a base 10 number raised to an exponent, allowing for easier multiplication of vast quantities. This law is a direct consequence of the definition of exponents. If am means a multiplied by itself m times and means a multiplied by itself n times, then am to an is a multiplied by itself m plus n times. The division law of indices. When dividing powers with the same base, the rule is to subtract the exponent of the denominator from the exponent of the numerator. This law is represented as a to n equals m minus n. Like multiplication, this rule only applies when the base numbers are identical. An example is 12th 8 made 12th 3, which simplifies to 12th 8 minus 3, resulting in 12th 5. This law helps in simplifying fractions involving powers and is frequently used in algebra to reduce complex expressions to their simplest forms. A common application of this law is seen in computer science, particularly with binary numbers. For example, dividing by powers of 2, like 2 through 5 2 equals 2 3, is analogous to bit shifting operations, which are fundamental to how computers process data. The power of a power law. The third key index law deals with raising a power to another power. In this scenario, you multiply the exponents together. The rule is written as amn equals akmn. This law allows for the compact representation and simplification of expressions with nested exponents. Consider 7 3 to 5. Applying the law, this becomes 7 3 to 5, which simplifies to 7 to 15. This principle is fundamental in areas like cryptography, where large numbers are raised to high powers, and efficient calculation methods rely on these index laws. This law can be extended to multiple nested powers, such as a square mnp equals a mmn p. This demonstrates the hierarchical nature of exponents and how they can be combined in a sequential manner. This section focuses on the special cases of 0 and 1 as exponents. Understanding these rules is crucial for simplifying expressions. Any non-zero number raised to the power of 0 is always equal to 1, a to the power of 0 equals 1. This rule is a direct consequence of the division law of indices, where am, a square m, a m minus m is a 0, and also a m equals 1. Conversely, any number raised to the power of 1 is equal to itself, a equal 1 equals a. This is intuitive, as raising a number to the power of 1 simply means using the base as a factor once. These rules are crucial for simplifying expressions and solving equations involving indices. The rule a squared equals 1 holds true for any non-zero base a. The expression 0 square 0 is considered an indeterminate form in calculus, meaning its value is not uniquely defined and depends on the context of the limit, highlighting a subtle but important mathematical nuance. Understanding roots, square and cube roots indices also encompass roots, such as square roots and cube roots, which are essentially inverse operations of squaring and cubing a number. A square root of a number x is a number y, such that y² equals x. Similarly, a cube root of x is y, such that y² equals x. For cube roots, the sign of the root matches the sign of the number. The cube root of a positive number is positive, e.g. cube root 64 equals 4, and the cube root of a negative number is negative, e.g. cube root minus 64 equals -4. Square roots of positive numbers have both a positive and a negative solution, but the principal positive root is usually implied. The concept of roots extends to higher orders, such as fourth roots, fifth roots, and so on. These can be expressed using fractional exponents, where the nth root of a is a square 1n. For example, square root of x is x square 1/2, and cube root of x is x square 1/3. Combining index laws and practice. Mastering indices involves not only understanding each law individually, but also knowing how to apply them in combination to simplify complex expressions. Always remember the indices checklist. Ensure base numbers are the same. Recognize that a number without an explicit index has a power of 1, and be careful when dealing with negative bases and exponents. For example, simplifying 3/8 times 3, or 3/4, requires first applying the multiplication law in the numerator. 3/8 turn 3u1 3/8 plus 1 equals 3/9. Then the division law, 3/4 equals 3/9 equals 3/5. This systematic approach ensures accurate simplification and avoids common errors. Regular practice with various types of problems, including those involving square and cube roots, is essential for building fluency. Familiarity with common square numbers up to 15 2'd, e.g. 169 equals 13/2, and cube numbers up to 10^3, can significantly speed up calculations, especially in non-calculator contexts.
Summary. Well done, you have completed the course, Index Laws, Powers, Roots, and Simplification. You should now be familiar with Introduction to Indices, Basic Laws of Indices, Powers of 0 and 1, Understanding Roots, Applying Index Laws. Should you need to revisit any of the topics in this course, please use the menu at the bottom of the screen